Welcome to the second course of the Basics of GNSS certification from Topcon University, GNSS 102, Differential GNSS Positioning. In the GNSS 101 course, we learned that the positions of GNSS satellites are constantly changing as they orbit the Earth. To get a latitude, longitude, and elevation position with any GNSS receiver, we have to track at least 4 satellites. Similar to a pirate finding his treasure using references to various objects, GNSS uses multiple satellites to triangulate the receiver's position on Earth. However, a single standalone receiver can only give us a position accurate on the Earth to a few meters, 10 feet or more. This is great for navigating our car to a specific location, but in construction and surveying we need tolerances of only a few eighths of an inch. To accomplish this, we need to understand more about GNSS signals, the errors that affect them, and the difference between a precision GNSS receiver and a navigational receiver. As explained in Section 1, GNSS satellites orbit the Earth at more than 12,000 miles elevation. During that long journey to our receiver's antenna, the signals have to penetrate the Earth's ionosphere and atmosphere and encounter other forces that can distort the signal. All these natural effects impacting the satellite signals cause the several meter error in the accuracy of a standalone GNSS device. If we could see the error that the Earth's atmosphere and other factors contribute to our GNSS position, we would see it bouncing randomly all around our receiver, changing every second and drawing a circle several feet in diameter, some very close to our actual position, others very far off. A navigational receiver can average these positions, shrinking the circle somewhat, but still our single unit error can be several feet. Fortunately, we can combine more than one GNSS receiver in a local area working together to minimize this error and transform position accuracy from a few feet to only a fraction of an inch. We call this technique differential GNSS positioning, and it is absolutely essential to precision GNSS positioning and guidance. This section will give you a basic understanding of how this works. Because of the high altitude of the GNSS satellites, if we have 2 receivers operating in the same local area, within 10 to 15 miles of each other, they will both be tracking the same set of satellites overhead. Even more important, the signal error that impacts one receiver will be nearly identical to the other receiver, both in the amount of distance error and the direction of that error from the true location. For example, one moment the error affecting System 1 is 7 feet to the northeast. At the same time, the error affecting System 2 will also be 7 feet to the northeast. The next second, the error on Unit 1 may jump to 3 feet to the west. At the same time, the exact same error, 3 feet to the west, will affect System 2, and so on. Because the error is the same in both size and direction on both systems, when we compare instantaneous positions from both units, we can compute the difference, or baseline, between both units very accurately. If the 2 systems are 1,000 feet apart due east, the difference between the 2 every second will remain 1,000 feet due east, no matter how much error is introduced. Thus the terminology differential GNSS positioning. Here's another example to help illustrate this point. Imagine we have 2 people standing exactly 20 feet apart holding a pole between them. If they both move 2 feet forward, the distance between them stays constant. If they now move 3 feet to the left, the distance between them remains constant, exactly 20 feet apart. GNSS error affects both units exactly the same on both ends. You don't have a 3-foot error on one end and a 5-foot error on the other. It's one thing to know the precise distance and direction between 2 systems, but we need the positions all relative to our fixed job site. So the next step is to hold one unit's position fixed, which we call the base station, while the other, called the rover, moves around the site. If one receiver remains in a fixed location, it can compute the exact error affecting our system at any given time. As the second system moves around the job site, the raw GNSS position is corrected by the stationary system as it computes the amount of error affecting both systems. Now, we can compute the accurate position of the rover unit relative to the base unit anywhere on our job site. Another advantage to differential GNSS is that we can use any number of rover units referencing the same base station. The amount of accuracy we can achieve between two GNSS receivers depends on the type of technology the receiver incorporates. Cheaper receivers, referred to as navigational receivers, don't include the ability to utilize all of the GNSS signals that are transmitted, and most of them only track the US-based GPS satellites. They also use cheaper, less accurate antennas. A good example of this is the GPS built into many mobile phones. We don't require fractions of an inch accuracy out of our phone, but position information within a few feet or so can help us find the restaurant we're looking for. For the accuracy and position we demand in construction and civil engineering applications, the receiver must be designed with more advanced components. High-accuracy systems track all of the available signals from GPS satellites, as well as all the signals from the other systems such as the Russian GLONASS system. These high-end receivers also incorporate much more sophisticated electronic design and precision antennas capable of resolving the GNSS signals down to centimeter accuracy. For more details on how these advanced receivers work and the different types of differential GNSS techniques they utilize to achieve such high accuracies, it's on to Section 2.